Okay, so today's lecture will continue with our discussion on file system. So far in the course, we have discussed about process management of operating system. We discussed about how OS manages memory so that different processes can be accommodated in the memory and they can be interleaved. They can be executed in an interleaved way. The third kind of management that the OS does is managing files. What are files? Well, they are data obviously generated through different applications, but this data is not a temporary data. Unlike what we have in case of memory, where the data that exists, it exists in the memory as long as the memory is given some power. The moment the power is withdrawn, the data that is present in the memory is lost. So that is why we call them as volatile memory. But what we want is a permanent data, a data that would remain persistently. And that is the reason why we made use of different devices to store this data. These devices are not only meant for storing data, but they're also meant to provide the data to the memory or to the processing unit. And we call them the input-output unit. So in addition to the CPU and the memory, we saw in the last few classes that how we have some input-output unit that are essential for providing the data. And in addition to that, we also saw some additional storage, which we call the secondary storage devices. They are also of different types. The secondary storage devices, which we normally understand or we talk about frequently, is the magnetic storage, commonly known as the hard disk. We in the last class saw the structure of hard disk, and we saw that the hard disk, which is the secondary storage device, we call that secondary storage because this is the storage which holds a larger amount of data, a greater volume of data. And the data stored here is, so it stores a greater volume of data. Why? Because the technology on which these particular devices are built, they are used or they can be used to store larger volume of data of the order of terabytes or even more. And the data is persistent. That is important. The data is persistent. That means even if you turn off the power, the data is not lost. This is what we call the secondary storage device. So overall, if you look at the computer system, which we have been doing so far, we have the processing unit, we have the memory that holds the running processes, and we have alongside a secondary storage device which stores data. We saw the structure of the secondary storage device, one of them. We also saw that there are multiple types. They can be character type, they can be block type. We are looking at a block type device. Block type device means the data that is stored in this kind of device, they are obtained not in the form of bytes, but a collection of bytes. We call them blocks. We saw the structure of these devices, and we saw one of them, which we commonly refer to as the hard disk. We saw that it's a set of disks that are arranged in the form of cylinders. That is, they are stacked one above the other, and there is a spindle that goes through. So they are moving along a spindle, and each one of these disks, they can rotate. Okay, they can rotate about the spindle, and there is an arm which contains different heads which touch these disks. So whenever an arm touches the disk, some data is read. And this is how, what is the data? The data is nothing but some magnetic spots. Interestingly, we saw that these disks are divided into a number of concentric circles called tracks. And these tracks are in turn divided into a number of sectors. This is how a disk looks like. This is the structure of a disk. So data in this case is stored in the form of blocks, right? This is the overall picture of the disk, or the data is stored as some kind of a collection of magnetic spots. Fine. So data ultimately, which is stored in the device, is in the form of blocks of data. What is the size of the block? It can be many. We'll talk about that. But on the other side, this data which is generated here, or it is generated in some process that is present here. This is the portion where the data is generated. When this process is actually running on the CPU, the data is generated. So what is the format of that data? Is it the same as this? No, it's in the form of some 1-0 combination. So the data that is generated during the execution of an application or a process is some 10, 10, 101, this kind of an array of bytes. So it's you can say an array of bytes. Look, so if you look at the application level, which is actually executed, it is some array of bytes. That's what the data. But the data that actually gets stored on the device is some blocks of magnetic spots. Well, so this is a huge transformation that takes place from an array of bytes, which is nothing but some signal or voltage levels, to some range of magnetic blocks. Okay, that's it. Well, that's fine, no problem. All of these zeros and ones are ultimately mapped to a magnetic spot present or absent. You can think it in this way. But the question is, when you say these are the array of bytes, this array of bytes will have a finite size. Either it can be of size kilobytes or megabytes or gigabytes, whatever. So this array of bytes will be of a finite size. When this thing will be stored here, it will also occupy that amount of space in the magnetic disk. No problem. So let's say some 1 MB space of array of bytes here will require some 1 MB space in the disk. But the question is, how will you keep these 1 MB data? Will you keep one by one? Will they be accommodated in one block? Will they be accommodated in many blocks? If they are accommodated in many blocks, are these blocks sitting one after the other? Are they sitting in a particular sequence? How are you managing this information? That this 1 MB data, which is a file, this array of bytes is what we call file. How does this sit in the block? So when I say that, okay, I want this file, which actually means I want this array of bytes, that is equivalent to a certain number of blocks. Are these blocks contiguous? That is, they are sitting one after the other, or are they sitting in a distributed form all over the disk? If they are sitting all over the disk, how are you managing them? How are you deciding where to find those blocks? Who manages that? So there is a requirement of proper organization of these blocks, number one. And number two, there is a requirement of this translation to happen, so that when I request for a file, I would eventually be taken to those range of blocks. And this is what is the job of file system. So this is the organization that helps you in managing this. So let's talk about in details the file system. Before we go into the discussion of file system, we will talk about some terminology. We have already seen that. I'll just quickly go through that so that you remember, and we'll be using these terms pretty often. So what is this basic idea? A file system, as you see here, if you look at the basic definition or the aim of a file system, you see that it is a way to manage variable size persistent data. This is the basic aim of any file system. Okay. Remember, file system is also part of the kernel. It may or may not be part of the kernel, but for the time being, let's assume that we have some special, organization, some special kind of, a software that would allow me to manage the data. It's like this. Here is your hard disk, which has certain blocks of data. Let's say this portion is some data. Okay, data 1. This portion is some data 2. This portion is some data 3. They are some data. And this, let's say, this is the portion of the hard disk that actually contains information about this data. Information means how are these data blocks oriented? What have you stored in this data? So you can think that these are some additional blocks which are the ones that are managing the show. They are the ones that are keeping information about that. So you can think that these are the blocks that typically form the file system. So the file system is also part or stored in the hard disk. Well, who manages that? This file system is managed by, or this file system is used or utilized by the kernel. So the kernel uses this file system to know about this data which is present here. It makes use of this file system. So we will first talk about the basic idea of file system. Then we'll see the architecture of a file system. And then finally we'll see different design procedures of file system. Okay. You may have a system that doesn't need any files. In that case, you don't need a file system. So somebody may ask you, do we really need file system for all systems? No, definitely no. If you are not dealing with files, you are only managing processes, you don't need a file system. You need a file system when you have files. When you have files and you will be requiring those files, you will be working with those files, then you need a file system. So it is a way to manage the data. How? What do you mean by managing? What is this manage? Manage means store and operate on the data. So a file system would give you the basic idea of how am I storing the data? How am I organizing them? How am I able to retrieve if I want some data? And how am I going to delete or remove some data? Storage, retrieval, and removal. These are the three things that you need when you are operating on a data. And file system provides you all this facility. Without this file system, it will be a random or an unorganized way, and it will be very difficult to work with files. Okay. File system also allows you random access, which means if you want to access a file, you don't need to know the details of the file. It gives you a very easy interface to use the file. And how do you access a file? We access it through a name. I don't need to know the details of what are the block numbers in my hard disk. I will simply request for name, and rest of that is taken care of by the file system. This is the basic motive of a file system, that it gives you to access any files wherever they are sitting in the hard disk. Not only the file, they will also allow you to access, or the file system allows you to access parts of a file. And this is very difficult because, as we have just seen, that a file may span across the hard disk. It may sit somewhere in the hard disk, some part, other part may be sitting somewhere else. So if you have to obtain a part, you have to go into the details of its location, which is again very difficult. That is taken care of by the file system. It just allows you to access parts of a file. So file systems are implemented on top of block devices. So overall, if I can draw a diagram, it will be something like this, that you have, let's say, you can assume that here we have some blocks. Okay, let me draw it in this way. Suppose here I have some blocks. Okay, these are blocks. I'm writing them as square blocks. Remember, they are blocks within a circular disk. Now, these blocks in turn are nothing but some records, let's say. So these are, you can say, some records. And here is the file structure. This is, say, the file structure. And here is some, user command. User makes use of some directory. Structure or file system structure, whatever. And this file system structure is through which you can have this report. You would have to access these blocks, which is very difficult. Even if you say I will not access blocks, I will put them into some kind of blocks. But even this is difficult. So what this file system or file system structure gives you is some access methods through which, by these commands and by making use of these access methods, you can manipulate these records. And manipulating these records in turn means reading or writing to these blocks. This is what the file system is supposed to do. Okay. Is this point clear? It is some kind of an abstraction for the application. Application wants to access.
Can you just explain arbitrary parts of a file can be accessed, that part once again?
Sure. A file, as you know, is composed of a number of an array of bytes. And that array of bytes finally sits into and forms a list of blocks. Now, when I want to access some part of the file, not the entire part, let's talk about some a database. When you are accessing a database, you may not require to access the entire database. And database is nothing but a collection of records. When you are accessing a part of the database, you are actually accessing only some of the records, not all. So that means you are accessing only some part of the file or some of the blocks, not all of them. And these blocks, as you know, can sit anywhere in a distributed fashion. So if you would have to do that going down to the block level, it would have been very, very difficult. So can I provide you some interface through which you can access only the relevant portion of the file? File system structure gives you that facility. We will see today.
So basically,
Okay,
like
this
in Windows,
is
so basically, like in Windows, when we open the C folder or D drive folder, and then when we open it, so the path that it shows, are we talking about those parts of the file system or the file?
you're talking about the path.
Yes, so means the components which are present in the path, if we refer to a particular
That is part
file.
of the file system. Whatever you are talking about C and D is some partition, and that partition is a collection of blocks. So see, the partition C or D, whatever you are calling, is a range of blocks. Okay, it's a range of blocks. Now, the data that is present in this range of blocks, you are able to access that through a name like C or D. You are not mentioning the block number or the block range, you are mentioning C. That naming methodology, that okay, if I am saying C, I actually mean this range of blocks. This is what file system has provided you. Now this C or D may have several files, and these files can be grouped into several directories. When you are accessing a file, then again, you are accessing a file through a name. You are not accessing it through its mention of bytes or through mention of blocks. So this is the facility that the file system is providing the user to access the file through a more simplistic access method, through just a name. Okay. We'll talk about
Yes,
how this naming happens in case. Just wait. Let's move ahead. Okay, so a more abstract is to access a way to access the information by name, like devices even are accessed through name. The process is accessed through name. For example, when we were looking at some command, let's say PS command, if you remember, what was it providing us? A list of processes that is running on the system. And we could get all information about the process. What is the number associated called process ID? What is the name of the process? And we were giving, when we type on some terminal, we give this command called Firefox. What exactly are we doing? We are giving a name to that particular process. We are accessing the process through a name. This easy way of accessing something, of especially the files, is what is the role of the file system. Okay, now, so we understand file system is essential for organizing and operating on files. Now, the files that we are talking about, or the device that we are talking about, is a disk, which is a non-volatile block addressable storage. You will get data in form of blocks. Block is a sector. Sector is the smallest chunk of I/O on a disk. It can be of variable sizes. Minimum is 512. That's the smallest block or the sector that is possible. Highest can go up to 4K bytes. A typical Western Digital Black Series 4 TB drive has so many byte sectors. This is about the structure of the block device. Now, this range of blocks or group of blocks we call partition. Okay, it's a group of blocks that you call partition. For example, someone just mentioned C, D, which you normally tell in Windows operating system. What is this C, D? They are nothing but some names that you have given to a range of blocks, right? It's a range of blocks that from this block number to this block number, these kind of files will be there. It's a partition that you have created within your entire hard disk. Your hard disk contains a lot of blocks. You decided from this block to this block, I will call or I will access that by a name called C. Beyond this, I will access it by a name called D. If it would not have been there, you would have to tell the block numbers, which would have been very, very difficult. This is the advantage of having a file system. Your disk, if you have not created multiple partitions, by default has one partition, the partition in which you are working, the range of blocks which you are accessing now. So a disk has at least one partition. It may have greater than one partitions. You know that you often divide your hard disk into C, D, E, and so on. Then comes volume. Volume is disks, many disks or partitions that contain a file system. That is important. When I say partition, I simply say that I divided that into a particular group. I said C, I divided into D, that's okay. But I did not keep any file system within that. I did not keep any method of organizing files within that. Suppose in C, that is the range of blocks that I decided and gave a name called C, I put a particular file system called NTFS. Okay. So what I have done is I have created a volume because I have put a file system within that partition. And this D, let's say I do not give any partition to that. I do not keep any file system, maybe. So it's a raw file system or a blank file system. I have created a partition in my disk, but I have not put any file system in it. Some say that, okay, you keep it, next time you may put within this partition something called ext3, extended 3 partition. What are these? We'll talk about later. Okay, so it may be this. Interestingly, a volume may span disks. So the volume where you have kept a file system means the organization, the type of files, the way in which the files will be kept. It may span across disks. It's not restricted to only one disk. Okay. We already know that. What is a track? Tracks are block tracks on a disk. Cylinder is the set of all blocks. If you take all the tracks of all the disks, you see that you get a cylinder. In the last class, we saw seek movement, which is the movement of the disk head from track to track, and the time taken by that is called seek time. In the last class, we saw different algorithms to reduce seek time. Now comes some important terms on the side which generates the data. First of all, we have a very common term called file. Everybody uses that. All of you know about it. So what is that? It's a unit of data that is managed by the file system. Something that an application has generated, an array of bytes. That has to be managed, right? Why? So because this array of bytes, which is generated by some application, is much bigger than, maybe much bigger than the size of one block. So that means this array of bytes has to be, kept or stored on a block device. So the question is, how will that be done? How many blocks will be required? Where will these blocks be sitting? When I will be requiring those blocks, how I will be accessing that? If I want to update a particular block, how will I be doing that? How will I access those blocks? Do I need to tell them as block numbers? Do I need to, or can I have a more simple way of doing that? So that basic unit that is actually stored, that contains the data, is called a file. And this is what a file system has to manage. The data that we are talking about, which forms a file, which is the content, that can be of two types. It can be an unstructured, which is a simple array of bytes without any order or any particular style of keeping the data. The second one is a more ordered way of keeping the data. That's called records. It's like tables where you have fields and their attributes, right? So the database that we commonly use, that's about a more structured data. That's called records. And unstructured data is which simply is a stream of bytes. Fine. So these are the two categories of data that you have: structured data, unstructured data. How do you access that data? How do you access that file? It is accessed through a name. Okay. So that array of bytes which you contain will have a name given to that. So we usually call the file name. And the file name to its corresponding content, this mapping is handled by the file system. Okay. But is it sufficient to have just this files? No. What we require is some additional information about the file, which we call the metadata. And this metadata is the information about the file, such as when was the file created, what are the permissions given. Permission means the read, write, executable permission. The length of the data, how big is the file size, which we commonly call. Why? Because the file size will give you an idea how many blocks will it require on the hard disk. The location of the file, which we usually call the path. Okay. And this is the creation time, the time stamp, we call that. When was it created? Why do you think is important? Because there are a lot of times we want to know that a particular file has been updated. What is the latest version of that file? Looking at the timestamp, you will be able to determine that. That's about the metadata. Very interestingly, this metadata is present in a data structure which is called Inode. This is the data structure that contains the metadata. Okay, so it is a data structure that contains the metadata about a file. So whenever an application creates a data and you have stored it in a file, invariably there is a metadata created of the file, and that metadata is stored in a data structure called Inode. So every file will have an Inode. So any application that wants to access a file first has to access an Inode. Remember that. So the moment you create a file, there is an Inode that is allocated. Whenever an application wants to access a file, it has to access its Inode. Until its Inode is accessed, the file cannot be accessed. Simple as that. Okay. Right. What is there in the Inode? Well, all this information that you see is present in the Inode. Attribute. Also a form of metadata. It is like a textual name and an associated value, like an author of a document or source URL, all this. The third very common term that we will be talking about is called directory or folder. It's also called folder. What do you have in a folder? Well, a folder contains, it's a container for file names. Let me give an example. You have a folder called desktop, right? This desktop is also a file, except that this file has no data content. Right? What it contains is a list of files and folders. That's what it has. It's a list. It's not an actual data content. It's not like a text or a media player. It's not like that. It's a list of files and some other folders. That's what it is. And this is what we call folder, all folders. So folder is also a file, except that the content of a folder is a list of files and folders. Okay. Now, if you have a folder within a folder or a directory within a directory, like S1 is a directory, within that I have a directory called S2. And within S2, I have a directory called S3. This is called a hierarchy of directory. Hierarchy, one within the other. Who is on the top of the hierarchy? S1. And who is at the bottom? S3. So this is called hierarchy. Now, if you have a hierarchy of directory, that is directory within a directory, you can arrange them in some, you can access them in a hierarchical name. How? Suppose you want to access S3. To access S3, you have to travel all the way up to S3 starting from S1. You can have a naming in this way. S1, within S1, I am going to access S2, and within S2, I'm going to access S3. So this is a hierarchical naming structure. We also call it a path to reach to a particular folder. Okay. Is that okay so far? The terms, it's very, very important to know all these terms because we're going to use them very frequently. Okay. Now, there's something called, now if I would like to show you the disk layout, then it will be very important. Let's say, let me draw for you the disk layout. I'm writing it as a rectangle. This is, say, what I'm showing you is a disk layout. But remember that it's actually blocks in a cylindrical disk. I'm showing you as if it's a rectangle. So if you look at this, if this is, say, this entire thing is a disk with number of blocks in that. So the first few blocks, I'm showing them as a group. This is the boot block. Now, if you remember when I was talking about how the kernel gets loaded onto the primary memory, if you remember, I told that sector 0, which is the first 512 bytes, is something called the boot sector, right? It's the boot sector, the first 512 bytes of your hard disk. Sector 0, that's the boot sector. And this boot sector, or we call it boot volume, whatever you call it, the boot volume. Now, this is the information about which particular kernel you are going to boot. That's the 512 bytes that get loaded during the boot. That is brought into the primary memory. And once that is brought into the primary memory, what you have after that is something called the super block. Okay, this part, the super block. What you have, you can think this to be a blueprint of the hard disk. Means it contains very key file system information. What are these? The key system information, most important ones. What does it contain? It contains information like, okay, how many partitions are there? Where are the partitions? What are the file systems that are present in these partitions? This is what is contained in the super block. It's a blueprint. It's like the most important thing. You get the super block and you know everything about the entire hard disk. This is the most important part, the super block. Okay. Now, after the super block comes the inode list. It's a list of inodes. There are a lot of inodes which are there. There are also blocks, right? Blocks on the hard disk. That's a list of them. What do you do with them? Well, these are the ones that will be used when a file is created. Suppose you create a file new. There's an application, you open a text editor and you wrote this file new. The moment you wrote a file new in one of the application, whether it is say a text editor or an MP player, whatever it is. The moment you create a file new, we know that this file will contain some array of bytes, and this file will have to be given some inode. So one of those inodes from this list will be taken and will be allocated to this newly created file. That is why it's important that a list of these inodes is maintained. You may ask, is it a certain there's an upper bound to the number of inodes that can be? Yes, of course. There can be only a certain number of inodes. The moment you run out of inodes, you cannot create a new file. That's the time when your hard disk would say that I don't have enough space, free some space, which means that I cannot allocate any more inode to your newly created file. So there's a list which is maintained, and one of them is taken from here and allocated to the newly created file. Okay. After that, you have the data blocks, the blocks that will actually contain data of your files. This is the structure of your disk. You have the boot sector, have the super block, have the inode list, and then you have the data. So what is this inode? Often called the file control block. It's a structure that stores the file's metadata and the location of the file data. It's a very, very important thing for a particular file. So whenever you are working with file, you are actually working with the inode of a file. Because inode will take you to the location where your content of the file is. So if I say that, okay, I have created a file called F1, there must be an inode of F1. So when I will have to access the content of the file which is named F1, I will first have to get this inode, scan this inode or read this inode, and here one of the entry of that inode will be pointed to the data block, that is one of those blocks here that contains the data of the file. Is this picture clear to you? How things are stored? It's very, very important to understand this concept. Okay. Next comes cluster. What is a cluster? Well, it is a logical block size that is used in a file system, which is equivalent to a certain number of blocks. As the name implies, it's a group. You say that, okay, these many blocks I will work together. So I call this as a cluster. Extent is the group of contiguous clusters. Take certain number of clusters which are sitting one after the other, and you say, okay, this is starts from here and ends here. This is called the extent. Is the terminology clear to everyone? Is it clear, all of you?
Sir, cluster.
Feel free to interrupt. Yes.
Sir, cluster. There is confusion in cluster.
Why? It's
Sir,
a number of blocks. You
sir, does
block. Yes, Siddhant, go ahead.
yes, sir. I had a confusion that in cluster the blocks that are in continuous, they all belong to the same file.
Not necessarily. Not necessarily.
So how do we decide that this is a cluster and this is another cluster?
It is up to the file system to decide that I will consider this to be a cluster. The cluster may span across files. It's not necessary that they have to be of one particular file. Say, for example, you're installing a file system within that. So it's a file includes many clusters. Okay. Suppose whenever you come across some, your hard disk becomes corrupted, it says that there's a bad sector, or the sum of the cluster has become corrupted. It's like there's a range of blocks that have gone corrupted, like that. It's not related to any specific file. Okay. Now comes, so we understand that, okay, these are the terminologies, and now comes, if you have to design a file system, what are your design choices? What should you keep in mind when you are planning to have a file system? First, namespace. What is that? We saw that file system gives us a facility to access files through names. That's what we call namespace. The question is, what kind of a namespace would you prefer? Would you prefer a flat namespace? Means there is only one level like that you have, there is only one directory and all files are within that directory. Do you want this kind of namespace, that whenever you have a file, say F1, F2, all of them will be within one level, that is only one directory. You will have only one directory. All files part of that directory. Question is, do you want this kind of namespace, flat, or you want this kind of namespace? Within F1 I have F2, within F2 I can have F3, within F3 I can have F4 and F5. Do you want this kind of a hierarchical structure? Which namespace do you want? Design choice. I can go for hierarchical, I can go for map, or some other kind of a namespace if you feel. That's the first question that you have to decide when you are designing a file system. How am I going to keep or organize my files? Will I be keeping all of them in the same directory, or will I be giving a tree structure or a hierarchical structure? Second, when I will be designing a file system, will I be able to identify individual devices? Yes, many times I need to. It's like I have individual devices such as A, B, C, D. So we have explicit device identification. You have separate names given for separate devices. If you see, we have SDA1, SDA2 in this way. So you are able to identify different devices through different names. Will you be keeping separate names for them, or will you be integrating them into one namespace? That's again a question. Different people have different choices. The third, the file type. What kind of a file will you support? System support. Will it allow unstructured files to be stored, or will it allow structured files to be stored? If it is unstructured, it will have byte strings. If it is structured, then there is a organized or a ordered way of storing. So there must be some pointers to take you to the particular file. What kind of a file system type will you support? Will you support one type of file system, or will you support multiple type of file system? That means your file system supports or allows multiple files. For example, ISO 9600, which is typically present in your DVD drives. So the data that you are stored in ISO 9660 is a compressed form of data which is stored in normally the file system used in hard disks. Sorry, in compact disks. Will you be using only one file system? My system has only one file system. I'm only using Windows, or I'm only using Linux, or I'm only using Mac. Is it that way? Or the block device allows two different kinds of file systems to be stored. We call it dual boot system, isn't it? We have Windows and Linux, both of them coexisting. Well, that means that it is either NTFS or ext3. Then comes metadata. What kind of an attribute should the file system have? Very important. What kind of attribute do you want? Okay. And finally, how are you going to implement that? How is the data laid on the disks? We are going to talk about all of these, if not today, tomorrow. And we are going to see the structure of, by looking at Windows and Linux, we will be understanding how these differ in case of Windows. And we'll not call them Windows, we'll be referring to file system, which is used in Windows, and we'll be using ext3 for Linux. Okay. Is it clear so far, the discussion? Please let me know if the discussion so far is clear to everyone. Okay, fine. Then, so now we understand that we need some file system to handle files, organize them. Obviously, the question is, what kind of operations we do on files? So let's talk about how does the operating system work with the file system and what kind of operations it does. If we look at the first and the foremost operation that you first have to need, it's called formatting. What is this formatting? It's a decision that you take that I will keep these kind of files. That is why it's called formatting. You decide. All of you must have formatted disks. If not your hard disk, at least the pen drive. And if you are working on a Windows system, very often you encounter viruses, and then you are told, okay, my pen drive is full of virus, I need to format that. Now, when you are saying that I want to format that, what exactly are you doing? What is the operation you are doing? So we are going to talk about that. Look, when I say that I am going to format a particular device, specifically a block device, what I am referring to is, I'm referring to a particular format, a type of file system I'm going to put on that particular disk. Now, formatting can be at different levels. It can be a very low level format that is usually done at manufacturing time. Users don't have much here. The low level formatting is the device manufacturer has already done some kind of an formatting when it was manufacturing that. For example, it will be able to identify the sectors. CRC region says the cyclic redundancy check to check whether there's an error while writing or reading. So these are already predefined. You don't have much to do in that. If you purchase a hard disk, you'll see that there's already some created sectors within your hard disk that is for CRC, that is for error checking, and some sectors is already there. So this is already pre-formatted, low-level format at the device level. We normally don't do it here. Our formatting starts from one level up, which is from this part. You partition. The first thing you do is you divide the disk. You divide into one or more regions. This is what you do. Here you have a disk. It's of, let's say, from 0 to some 4 GB. And you decide, okay, I'll divide this into 3 or 4 halves, 4 parts. Okay, 1 GB each, I decide. That's the first thing you do. You divide it into number of regions. And then you decide, what will I do with these 4 regions of my hard disk? I say, okay, I will keep each one of them, you will have a separate file system. Okay, for this part, I say that I will keep this as, let's say, NTFS file system. And here I will keep ext3. I can. This is what you call partitioning, dividing it into different halves and putting a specific file system into that. When I say I am putting a particular file system, I'm forcing that I will keep data of this particular type. I will organize the files in this way in this particular partition. This is what I am deciding. What is high level formatting? You initialize a file system for use. We will talk about that later on when I'll be talking about file system in user space. That's what we are calling as use. What exactly do you mean by initializing a file system? Just the definition is mentioned here. We are saying that that's called high level formatting. What do? You initialize the size of the volume. Number one. Volume, if you remember, we said that the partition in which you are keeping a file system. The moment you are keeping a file system, you are first initializing the size of the volume. What amount of partition you are keeping for this file system NTFS? The range that you decide, this will tell, okay, this is the initialization. Then you determine where the various data structures would live. What do you mean by that? Well, I mean, where will be my free blocks? Where will be my inode list? Where will be my data block? I just told you, isn't it? That when you are having a disk layout, you are first having the boot sector. So forget about the boot sector. Then the super block, done. Now, when I'm saying that, okay, this part is where I'm going to keep my file system, then the first is my inode list. So different file systems will have different ways of telling how will you keep the inode, how will you keep access them. We will talk about 2 different mechanisms tomorrow. So don't worry, then you will get to know how 2 separate file systems are different. We'll talk about NTFS, or maybe we'll be talking about FAT32, and we'll also talk about the indexing system used in Linux. And then we will understand how 2 different ways in which files are accessed in 2 different file systems. And you initialize the structures to show an empty file system. Yes. So file system, the moment you have put a file system within a partition, you have to initialize something to tell that what is the size of the file system, what kind of files are there. Okay, this is what. Please, if you find anywhere anything which is very confusing, please interrupt me. I will be happy to repeat that. I hope so far it is clear to everyone, the idea that we are gradually moving toward. So the first thing, if you are handling or if you are working with a file system, you want to design a file system, the first operation that a file system should do or is required to be done is formatting. Formatting is the process where you initialize a partition or you put a file system into a partition and you initialize the file system. That's what we call by formatting. Simple. You put a file system within a partition and you initialize the partition. That's the first operation. Number two, second most important operation, mounting. Many of you have heard this term. How many of you have heard this? Mounting. Anyone who doesn't know? Okay, Pankaj says yes. Whenever you plug in a pen drive, and then after you have done your work, you want to take it out. It says eject. In Windows, it says eject, or in some cases, it says unmount. Right? Have you ever wondered what exactly is this term called mount or unmount? And if you don't eject many a times, it doesn't work next time. How many of you experienced that? You simply take, say, some power got turned off, or you simply, plug that out. Next time you try to plug in, it does not detect. Right? And it says it was not properly mounted. What exactly is the system telling us? Anyone? You know what this thing mounting means? No. None of you? No one knows mounting? Yes? No one is aware of mounting. Okay, fine. Let me explain. So mount is a system call, number one. Okay, it's a system call. What do you do with it? It's an operation, remember. So you have to do something with this system call. What do? You pass the file system type. Okay, and you pass the block device and the mount point. Three things. It's like this. Mount is the system call. What do you pass on? The file system type as the first argument, comma, the block device as the second argument, and the mount point as the third argument. What is this mount? Let's look at the step. First, simplistically put, it allows you to access one file system from the other. One file system from the other. How? Well, one device may have a particular type of file system, and the other device may have a different kind of file system. You may not be able to access that. For example, if you have a pen drive, right, which is having a particular file system on its own, and your computer or your laptop has its own file system. Now, how will the computer, your computer, desktop or laptop, how will it be able to access the files present in your pen drive? You understand the question? These are two different devices. They have two different ways of storing or organizing the files. When you are going to access the data or a file of your pen drive from your laptop, how will that happen? So the mechanism to do it is, first, make the content or make the file organization of the hard disk of your pen drive part of the file system of your hard disk. That's the first thing to do. Make it a part of that. And this is where this mount system call works. So look at the step. First thing, you access the raw disk. Which disk? The block device. Which block device? The block device to which you are going to attach. One is getting attached, the other is to which the particular file system is attached. So block device is the one to which you will be attaching a new file system. First of all, read the super block and the file system metadata. What is the metadata? Well, the list of those bitmaps and root directory, etc. Then third step is to check if the file system was proper, which is the check that you perform, whether previously when it was mounted somewhere, has it been properly unmounted? I'll show you this. It's basically something like this. Let's say this is like slash, within that you have something called home, within that you have, let's say, student, and here you have IIITA, and here you have, let's say, a folder called desktop, and this is what is there in your laptop, and here you have some file system called A, within that you have B, then we have C and D. This is what is there in your pen drive, the USB. Now you want to access this D, you cannot do that until you make this, D part of this structure. How? So you just have to take this D, you have to take this entire thing and you have to attach it somewhere. Maybe I will attach it here. Okay. So if I attach this thing here, now you see it behaves as if there's one single file system. And now, if in your computer you so far were able to reach desktop, it is like slash home slash student slash desktop. You so far reached here. You could access it here. Now, if you attach this to this desktop, it means this A gets attached to desktop and A becomes hierarchically lower than desktop. And then you can go on doing within A, within B, within that D. That's how you can. See how we attach this one file system to the other. This attachment is what is done through mount. Logical attachment. As long as you want to attach and make use of that, you attach it. When you want to remove it, you apply unmount, and then this link gets cut off. But if you have not properly unmounted, or you have not logically cut that off, and you again want to use or mount it to somewhere else, some other file system, it will say, hey, you did not have unmounted it, so first do it. That is why there's a check to see if the system was properly unmounted. It is clean. If not, then you validate. Once you have done that, then you will prepare an in-memory data structure to access the volume. That means you prepare this logical structure in memory. It means a data structure that is created in the memory, that is in the primary memory. So the primary memory will now have an view which is one complete or a composite view of the entire file system, where the lower one is also attached. Okay, and the super block is dirty, means the super block is in use. Whose super block? Well, super block of this file system. The super block gives you an indication of what is there in the rest of the disk. So if a super block is, show you so this is the reverse process where you are detaching a particular file system from the other. That can only happen if there are no processes with open files. Very, very important. Very often you see when you try to unmount a pen drive, it says I cannot unmount pen drive. There is some process which is already using that. Suppose your pen drive has some PDF file which you have clicked, and you have clicked it and opened it from the USB. So the particular PDF is already open, and then you try to take out your USB. It says, I cannot unmount, some process is preventing it. What does that mean? It means there's an Adobe Reader process which is currently running, and that has opened a file, and that file is part of the file system which is already being mounted. So until you close the process or you kill the process, you cannot unmount it, because some existing process is utilizing your file. So that is the first step of unmounting. Ensure that no process with open files in the file system that you have attached, is any process using that? If it is using that, first kill the process, then unmount. Once done, remove the file system from the OS namespace. Well, the OS namespace is the hierarchical structure or the nomenclature or the way in which your OS understands the file. Then we said that the file system basically gives you a named method of accessing files. So if you have attached a particular new file system to the previous one, you remove that naming part of the lower one, the one which was attached now, from the existing names of the files and folders. Flush all the in-memory file system state from the disk, because the in-memory, in the primary memory, there was a data structure which was created to keep track of the files of the mounted file system. Remove that. And the super block will now be mounted as clean, that is, unmount has taken place. So unmount taking place means that the super block has been retrieved or put back to clean. Okay. File system validation, that's the third, or rather the fourth operation that we are talking about. Now, OS performs some file system operations in the memory first. Okay, like block IO, it goes to buffer cache. If you remember, in the last class, I told you there's something called buffer cache. What is buffer cache? Some part of the memory you keep for holding the blocks. Why? Because if you know that these blocks are the ones which will be frequently required when you are accessing a file, why do you need to access them from the disk? Why can't you do it from the memory? So the place where you hold the commonly used blocks is what we call buffer cache. Now, not all blocks might be written to the disk. If the system shuts down or crashes or the volume is restored, it will leave it in an inconsistent state. Yes, because you are suddenly writing something to the disk and suddenly the power turns off. It crashes. So what will happen? Now, half of your volume has been written and half has not been written. That will lead the entire file system to be an inconsistent state. It's a very, very tricky situation. Okay. Then there are different file system.
Why do we need buffer cache? Means we can directly access the blocks from the memory also.
That is the whole
Means
story.
But just for the sake that of fast transfer, we are using buffer cache.
Correct.
Okay.
Because if you are using similar kind of blocks, there is no need that you will be accessing the blocks from the hard disk, which is a slow device. Why don't you keep the content of that in the buffer cache so that you will be able to access them from the primary memory? You don't need to go to the disk to access to improve the performance. Okay, so what is this file system validation? What are the checks that you do to validate that the file system is indeed correct? First of all, you will match the size. Okay, so you will find whether the file size matches to the list of blocks allocated to the file. You know that every file will be given some blocks, that these are the blocks which will hold the file content. Now you will see the size of the file and the total amount of size when each block size is added. Are they matching? If they are, fine. So it's correct. Second is you check the path name. How? We often check whether a file exists or not. What do? I already told you that. We will see the directory entry later on. So you go on searching something called path name. Path name is, as you know, it's like, suppose I am looking at a file called F1, which is this within this, desktop. This is called the path of the file. This is called the path of a file. Now, when I am traversing this path, I am actually traversing one inode to the other. This is an inode of the root. So I'm writing it as inode of root. What does it contain? Well, inode of root contains all the folders within the root. Suppose within the root there is a folder called home, dev, opt. So if you look at the content of this inode of root, you will find that it is like home, the inode number of that, dev, the inode number of that, opt, the inode number of that in this way. So when you will move from slash to slash home, you are actually scanning the inode of the root and you are finding out, is there any entry called home within this inode? Yes, there is an entry. So if it finds the entry, try to understand. This is the first inode that is searched, the inode of the root. The root of inode is scanned for all the content. What is it searching? It is searching the next character, that is the next string that is written after the root. It is looking at this string and is performing a string match to the entries of this slash or root. It's a simple string match, that's all. So all the strings which is there, home, it's matching with the each entry of this, content of this inode of root. If it matches, then the next field after that is what is accessed. And what is this field? The inode number of the next folder, which is within root. Here it matches. So this inode number is traced and it jumps to the inode of slash home. That is why we are saying that it is an inode list. It's a list, linked list of inodes. Comes to inode of home. What is it searching within home? It is searching within home the different entries of. Within home, you can have maybe student, then you can have desktop. I missed out. There should be a there should be some student here and then desktop. So home, student, desktop. So suppose this is some kind of a student. Again, the same procedure. It's a recursive program. Once I have reached to the slash home inode, I will start scanning the contents of that. And I will perform a string matching of this string, student or star. If it matches, I take that entry and I move to the next inode. What is this inode? It is the inode of slash home slash start. And again, I repeat this entire process. I go on doing this. So what basically you're doing is you're moving from one inode to the other and you're performing a string matching. Why you are performing a string matching? Because you are actually moving from one directory to the other. When you finally reach to the directory which contains the file, and then you perform a string matching of that file and you say that yes, desktop has F1 and F1 is a file. Once you reach to the content of F1, now the inode of F1 will take you to a data block and not to any other inode of directory. Once you reach to a data block, you read the data block. That's how you perform path names. So directory entries point to valid inodes. That's what I'm showing you. They take you to the inode of that particular entry of the directory. So it's a proper parent-child links and no loop. There is no loop. You go from one to the other until you reach to the leaf of the path, and that leaf of the path is the file. And once you reach to the file, the inode corresponding to that will be the data. What else? You have connectivity information like unreferenced files and directories. What is this reference? We'll talk about that in just a moment. Then we have some link counts. Now, what is this link? Well, files can be accessed through multiple ways. It's not necessary that, let's say, you think it in this way. Suppose there's a data block that contains some content. So this is a file content, right? There is an inode of a file. So I'm writing it as inode of a file called F1, whose data content is this. So data block of F1. So the rule says that this is the inode and this is pointing to this data block. If you reach here, you will be able to access the content of F1. That is how files are accessed. Now, link says that, well, I can also create another inode and I can also link it to the same data content. Okay, I can also contain another inode called F2 and I can link it to the same. So that means either I can access this data by F1 or I can access it by F2. I have two links through which I can access that. That's the way. Now it's called hard link. This is a hard link. Okay. That's one way. The other way is that I create an inode, but this inode will not directly connect to the data content. Rather, it will be pointing to the inode of F1. It's like this. So F2 will be pointing to the inode of F1, and once I get F1, I will be reaching to the data. This is another way. So either you can access this entire data content by F1 or you can access it by F2. This is called soft link. Soft link. Can anyone tell me an example of this soft link? We use it very often. You know that. You use it. Especially who work on Windows. Can you tell me? Have you seen accessing a file through two different file names? Have you ever done that? Give you an example.
So reference, you're talking about alias names that we create. The file.
Is there a situation where you could access a file from two different places in
Yes,
the
sir.
same directory?
So,
In two different places. Pankaj says shortcuts. Yes, shortcuts. Absolutely. Shortcuts are this. That's what we call a soft link. This is what is happening. We create desktop shortcuts. Whenever you install something, the software automatically creates a desktop shortcut. So do you see that the shortcut, have you clicked on the properties of the shortcut? Go and click that. You will find that the shortcut contains a mention of the actual path of the file. It is just a shortcut. That is, it is just a link, soft link. That's all. This is what is it talking about. That how many links is there to this inode? There can be many links. I can create many links to this. How many links have you created? So this inode will also keep a track of the count of the number of links that is coming to that particular inode. So fcheck will also keep track of that. Then it will keep track of bitmaps. I'm not talking about bitmaps now. We'll talk about that later. As I've already told you, this is how you build namespace using mount. Already mentioned, pictorial it has been shown. Let us assume that there's a volume by the name /dev sda1. And this is the volume /dev sda2. It's very, very common. This is the hard disk that you normally have, and this is the external drive. So whenever you mount an external drive to your system, the system, you know that as you give a name C, D, whatever, but the system actually treats it by the name SDA2, and you see it is within / device. DEV stands for device, within that SDA2. So SDA2 is the name given to that particular file system. That device that contains the file system. And SDA1 is the device that contains some other file system. You want to attach that. Look, this entire thing gets attached to home. How will that done? You said mount the command -t to attach that. Attach what? To. So it is of type mount -t tells you the type of file system that you are going to attach. -t should be followed by the type of file system that you are going to attach. So this is the file system that will be attached, ext4. So this file system is of type ext4. So you are saying mount a ext4 type file system which is present in this device to this particular position within the file system of SDA1. I repeat, mount a file system of type ext4 to the point /home within the device or of the device /dev/system. So /home becomes the mount point for this. So this you are mentioning as mount point. So if I summarize the entire command, it is mount -t followed by the type of file system, followed by the device which is going to be attached, followed by the mount point of the file system in which the second file system will be attached. Which place in the file system 1 that you are going to attach it. This is the mechanics. After you have mounted, this is what it looks like. And now the slash is no longer visible because now it has been mounted from here. So /home Paul and /home IEEE or LE are no longer visible. Why? Because they are overwritten by this file system. So this part, this and this now are overwritten. Anything below that is now overwritten by this. So it is very, very important to know where am I mounting. Usually when we mount any new file system to my existing file system, we usually mount it to a particular point which has no directories below that. And Linux uses default something called /mnt. It usually mounts it here within /mnt. You don't have normally. So as long as you are working with that particular file, yeah. Pranav, you want to ask something?
Sir, but won't it lead to data loss if it is overwritten?
It's not overwritten. Please don't get confused. It's not overwritten. It's just for that particular time it gets mounted. So everything below that home is now inaccessible as long as your SDA2 has been mounted. The moment you will be unmounting, you will get that. So you should be very careful where you are mounting it. You should be mounting it to a point where there is no other subdirectory so that you can access it. Okay. Usually it's somewhere here that there is an MNT which is blank, nothing below that. Here, if you would have mounted, it would have been better. Then this would have also been accessible. Just to show that what can go wrong if you just choose a different mount. Union mount. Well, that the example. If I would like to attach it and at the same time not lose the file system which was already there, I call it union mount. That's what you see. So we should take up these operations and then. Okay, so let me summarize. How many operations we have completed? We discussed about format. We discussed about mount. We discussed about unmount. What else? We discussed about check. So we discussed about all this. Okay. Now we are left with the basic operations. Creating a file, reading a file, writing a file. Let's see what happens when you perform these operations. Is it clear so far? I will be waiting. I'll take some time to just take any questions if you have. Is it okay so far? Class? You can understand whatever operations we're discussing? Okay, that is so. And let's move ahead with the next one. Creating a file. What is this? Well, creating a file, as I've already told you, whenever you create a file, you invariably have to create an inode for that, because that is the container that contains the metadata. So you create an inode to hold the metadata about the file. That's what we mean by creating a file. Create a metadata means there's an inode that is already there. One of the inode gets allocated to that file, and the data about that file is now written into that inode. What is that? First of all, you initialize timestamp, which is the time at which the file is created. That information gets recorded in the inode. Every inode has an inode number. Please remember that. Every inode has an inode number. The moment you create an inode number, the inode gets the number of that inode gets allocated, and that is attached to a particular file. A timestamp is written into that. The file is created at this particular time. Permission is given. Okay, permission means what kind of a file? Read, write, executable. So this is like read, write, executable permissions. What permissions have been given? Mentioned in that inode. Size is initially 0 because you have not written anything. There is no data block that has been written with something. You just have created file new. File new will actually do this step. Now when you start typing, still not done. When you do file save, right, then some data blocks will be added and this size will be increased. When you do file new, the inode is created. When you do file save, the data blocks, that is the data content that you have written in the file, they are put in the data block. The inode is updated. The size is updated. The pointers are updated. And then the data block and the inode is now put in the respective position. This is what happens when an inode is created. Well, not enough. Apart from inode, the file should also be part of a directory. It has to be part of a directory. So the moment you create a file, you add a directory entry for the new inode. You may say, sir, but I just created that. How can that be entry? Oh, there is. You see, if you are talking about the ext3 file system, everything starts from the root. So if you create a file, you invariably, if you have not created it anywhere, you would have done it within root. So the directory entry of root will now have your file. If not, if you have done it within home and student, and here if you have created this file f1, so file new, I gave a name called f1, this eventually created this. This f1 is now an entry of the directory student. So if you look at the inode entry of stud, it will have f1 and the mention of its inode. So the inode that was given to f1 let's say number 1526. So F1 start will now have an entry called F1 and we'll have 1526 as one of the entries of F1, the inode number of F1. Every file that you create will have, let's understand this. The moment you create a file, there's an inode allocated to that, and there is a directory entry maintained in it. What will that directory entry have? The name of the file and its inode number. What will this directory entry be? As you see, set of file name and inode number. That's what I've written it. Right? What else you will have in every directory? You will have a dot and a double dot. Dot is the current working directory. It's called CWD. The current working directory, the directory in which you are, its inode number. And what is double dot? The parent working directory. The one which is above that. What is the parent of start? Home. What is the parent of home? This. So what will the dot dot contain? The value of this dot dot? It will be the inode number of home. And what will be this? The current working directory, whatever you are, in whichever directory you are. If you are currently in home, it will contain that of home. Right? So every directory entry, in addition to all the files and folders, the entries of files and folders and their inode numbers, has two other entries: the current working directory inode and the parent working directory. So just look at the directory entry. This is what has. It has a file name and inode number. That's the entry. Okay. So current working directory, or you call it path name, is used to specify the file name. Okay. Directory is just like a file. It's name inode pairs. And what is the way to create that? The moment you want this command, mkdir, say I create a command called play. That means I want to create a directory. The moment I type this command, very similar to file, an inode will be allocated to it. This will be an inode of play, right? And it will contain some, entries. What entries will it have? Well, it does not have any data block. What does it have? All the folders below that. Currently, it has no folders within that. So what minimum two entries it should have? Because play has just been created, I have not created any files or folders within that. So minimum two content will be there. One is dot and the other is dot. What is dot? The current working directory. Dot dot, the parent directory of play. Here inode numbers. Is that okay? Links to files. I've already mentioned that. I have told you just a few minutes ago that it's not one way that you can reach to it through links. And there are two links that we have. One is called symbolic link, where the file's content, it contains a link to another file or directory. Say, for example, this is the alternative of shortcut. In Windows, we call it shortcut. In Linux, we use this symbolic link. If you have used it this way, it will actually mean that new file name. So current file is a file name. So there is an inode corresponding to that. And the inode new also having file name and inode created. But inode will not directly connect it here, it will connect it to here. And via this it will be connected. So there are two ways in which you can access the data content of this file, either by giving, let's say, I want to see the content. I can give cat current underscore file, or I can give cat underscore file. both will give you the result. But the problem is, if you remove this, if you delete this suddenly, this means this deletion. This is so this becomes hanging because this is over. So where is it going to? It keeps dangling. It's called broken link. Try this out. If you have created a shortcut and the original file is deleted, your shortcut now is pointing to a null pointer. It does not know where it is going to point. It's not null, it's a dangling point. That's the problem. But what is a hard link? Or we often call it alias. It's this. Here, have the current file and the new file. In this case, both are pointing to the same. Both are the current file. This is new file. Now both are pointing to the current file. So we have two inodes and each one of them. So that even if this particular CF, which is having an inode to this, even if this is deleted, still you can access it via this path. Okay. Now you may wonder, when will this stop? Well, when all such links have been removed or deleted, your link count becomes equal to 0. Right? So you keep track of how many links have been connected. When all the links have become 0, then only your file is deleted. Please try to understand. If you create hard links, and when you create hard links, if all the links are still existing, even if you delete one of them, the file does not get deleted. You can always reach it to the second file. When all hard links have been deleted, only then your file becomes. How do you keep track? You keep track through a counter. When the link count becomes 0, that is, no more links are there, it becomes 0. I could have shown this, because due to lack of time, I'm not able to show it. So this is what we have. Now I'll stop it here. I'll take your questions now. And tomorrow I'll take up the second part, which is we already discussed today about links, etc. So now we are left with the most important operations, that is reading, writing. Before that, opening a file. We've already seen some library calls through which we work with files, and now we'll see the details of that. So tomorrow we'll talk about that in the first lecture, and the second lecture we'll talk about some file system implementation, how the files and their, the data blocks, how are they allocated. So that's what is going to come tomorrow. So that is all for today.